Last week we talked about the atmosphere as a whole, looking at the different layers of it, different components of it, what makes it up, what kind of chemicals are in it. Uh, and we learned a little bit more about observations and how we can pick up uh, what's going on in the atmosphere, not just being at the exact spot in the atmosphere, but by remote sensing, such as satellites or radar. This week, we're going to talk about the engine that basically fuels the atmosphere, what causes it to behave as it does. So the atmosphere would do nothing if it didn't have energy coming into it. And the energy that comes into it is the sun. The sun supplies all the energy for our planet so we can live here. The atmosphere moves, creates storms. So the first step in understanding weather is understanding a little bit about the solar energy that comes in. And believe it or not, the Earth emits energy as well, called terrestrial radiation. So let's delve into some of that right now. So, how does the energy flow into and out of this atmospheric system, and what keeps our temperature, on the whole, relatively stable? So, here's the electromagnetic spectrum. Uh, when you look outside and you see light, some of that light has come from the sun, but you don't see the sun's radiation, you see Earth's radiation, reflected radiation typically. Uh, so, with that in mind, what you're looking at here is the various wavelengths we see. And notice that looking at the electromagnetic spectrum, we're really only looking at a small part of it that we see. Right in this area here are our colors. Here you have infrared, which is more radiation from the Earth. Here you have ultraviolet, which is more radiation from the sun. And then you have things like X-rays that help us look into our bodies to see what's going on, help the doctors make things, understand things. There's gamma rays, there's radio waves, all of which are part of the electromagnetic spectrum. You'll notice that they're kind of divided by how they're used. In other words, we look at shortwave radios or AM radio broadcast, infrared radiation from the Earth, microwaves, X-rays, all of which have a certain wavelength that implies what their uses are. So what's a wavelength? Let's talk about that first. Well, energy goes in an up and down path. And from one crest of the energy wave to the next is a wavelength. So if I was in the ocean and I had a wave strike me, that would be the top of one crest. The water goes down as it's flowing by, then goes back up again as the next wave hits. That is the distance between those is a wavelength. Now, electromagnetic radiation waves are a lot tinier than ocean waves. And interestingly, they all move at the speed of light, or 186,000 miles per second, moving pretty quick. So, with that in mind, the shorter the wavelengths are, electromagnetic radiation, the more energy they carry. So, think about it when you're seeing electromagnetic spectrum and you see the wavelengths that we just looked at, the closer those wavelengths are to each other, the smaller they are, the more power that energy has. So that's why gamma rays are very powerful. They're very tiny wavelength. Black bodies. What are black bodies? Well, they maintain a temperature that's constant, and if they are truly a black body, they absorb all radiation that it receives and then emits it all back out as a different form of energy. They're perfect absorbers and perfect emitters. However, none of that exists in the Earth. However, we can approximate them as being close to that. That's how we can solve some equations that are based, would be very, very complicated if we didn't use it this way. And since the difference is tiny, this way we can make use of something such as in a black body radiation, the intensity of it is inversely proportional to its absolute temperature. So the higher the temperature, the tinier the wavelength. That's why the sun emits some of the smallest wavelength. Temperature is extremely high. The Earth, on the other hand, would be emitting much slower wavelengths. And here you can see the displacement from the different wavelengths depending on temperature. Notice lots of visible light and all there, pretty much from looking at the sun's radiation. Okay, the total energy coming out of a black body is the fourth power of its temperature. Well, so if I have a temperature that was 10 degrees, 10 times 10 is 100, 10 more is 1,000, 10 more would be 10,000. So that would be your energy, 10,000. So 10 degrees Kelvin would give you 10,000. However, think about the sun. It's thousands and maybe even almost a million degrees in spots. So the amount of energy coming from the sun is way higher than the amount of energy coming from the earth. So the earth is a certain distance from the sun. And we say that, okay, there's a certain amount of radiation equals earth. Well, if I double the distance from earth out, it's inverse square law, which basically says the radius, if we double it, is squared. So that would be 4. So it would be 1/4 the amount of energy. If it was, say, 6, 1/6 of them further out, that would be 1/36 the amount of energy. Not much. The energy just goes down very quickly as you go out in the solar system. All right, here may be one of the most complicated concepts. It takes a little bit to think about. The sun is directly overhead at the equator on the equinox, or March 21st, September 21st. So at the equator, the sun is directly overhead. If you took and looked straight up in the sky at noon, the sun would be directly above you. Now, that happens, and the sun moves north during the spring, and moves south during the fall. So, with that in mind, the sun only goes up to 22.5 degrees north and 22.5 degrees south. So those are the only latitudes within there that have the sun directly overhead. Nowhere else does. So that's first and foremost. In other words, where we live, we do not have the sun directly overhead. However, when the sun's closest to us, the angle that the sun is hitting our area is much less than when its sun is way down in the middle of winter. So with that in mind, look at the flashlight picture here. If it's directly overhead, the sun's very intense. The same amount of energy is coming out of that flashlight, but much smaller area. Now, at an angle, notice the area spreads out. That is why, if you live near the poles, you're going to have significantly less radiation coming from the sun than if you live near the equator. That's why the poles are colder and the equator is hotter. And here you can see it. And remember, the sun is moving north, basically starts moving north after June 21st when it reaches this, December 21st, it starts coming back to the north. So that is why as time goes on into this late winter, into spring, the sun is getting more and more powerful. And here you can see the amount of radiation. Rockport, New York, for example, much more radiation in the summer, much less in the winter. Antarctica, no radiation in what would be our summer, much more in the winter, almost as much as Brockport, Maine gets in its summer. Singapore, which is right along the equator, gets pretty close to the same amount of radiation all year long. So why does this happen? Well, take a ball. Here you see the axis going through it. center of it, and our Earth is tilted. So as it's sitting here, it comes right into the equator. As it moves here on December 21st, notice it's coming in to the southern part. If you go back over the summer solstice, June 21st, it's coming up to the north because that's pointed towards the sun. So that's how the sun, even though the sun does not move in relation to the earth moves in relation to the sun. That's why we have different amounts of radiation. So we got to account for all this radiation. What happens to it? Well, things that can happen to radiation are it can be absorbed, it can be scattered, or it can be reflected. All right, so scattering means it's just going in all different directions. So here is an example of scattering. Actually, you see it every day when you look out at the blue sky. The blue sky we have is due to the scattering of radiation that's occurring when the sun's rays hit our atmosphere. They can also happen from clouds, particles in the air, whatever, all of that. But it just means the radiation goes in all different directions. Albedo, kind of a form of scattering, but a particular one. It just means that everything is reflected back. In other words, like it's having a mirror sitting there and just reflects all that radiation back in some direction. So that's albedo. And we have things that have very high albedos on the earth. For example, if you look at ice and snow, if you're out in the wintertime after a fresh snow and the sun comes out, you really need sunglasses on. That is because of the high albedo. Absorption, when radiation is absorbed. A lot of radiation gets absorbed in the stratosphere where we have ozone. Some of it does get absorbed by the ground in the atmosphere as it's going down. The lighter the surface, the less solar radiation can be absorbed and the higher the albedo. If you are living in the snow-covered regions in Canada, this picture shows, lots of radiation is getting reflected back into space and back out towards the sun. Down here, Great Lakes, where it's dark, or over the United States at this time, it's going to be warmer because it's absorbing much more radiation. Here's the totals. Reflected by the Earth's atmosphere is 30%, 23% gets absorbed in the atmosphere, and another 47% get absorbed by the Earth. And here you can see the principle where the radiation is being absorbed as it's coming down and what wavelengths that might be. So we know that there is pretty much an equilibrium on the amount of energy coming in, the amount of energy going out from infrared. One extra thing contributes to this, because if you didn't have greenhouse gases, we couldn't inhabit the Earth. It would be too cold. So greenhouse gases can be a good thing. Matter of fact, they're necessary. So what's a greenhouse gas? It's a gas that absorbs infrared radiation. It does not absorb the sun's radiation or the ultraviolet. It's absorbing infrared radiation. So as that energy is coming into the atmosphere, it's getting transmitting right on through these gases. However, once it gets to the Earth, strikes the Earth, gets absorbed by the Earth and changes back into infrared radiation, those same gases absorb it and transmit some of that energy back to Earth, keeping us warmer. The principal greenhouse gas is water vapor and then carbon dioxide. Methane and ozone also contribute. So with that in mind, let's take a look at what water vapor actually does. If you lived in the desert, you have very little water vapor in the atmosphere. I'm going to say you're at the same latitude as, let's say Georgia, but except you're in the west, you're going to be in Arizona. The sun strikes you, comes through all of that, and gets absorbed by the earth. It gets quite hot. At night, no sun's energy, all that radiation goes back out, no water vapor there to absorb any of that radiation, and it gets cold at night. Maybe down where it had been 100 during the day, it's down in the 40s or even 30s at night. However, if I go to Georgia or the southeastern United States, we got lots of water down there. So with that, During the day, radiation comes in, warms up. Now that water grabs that radiation at nighttime when it's going back out, and our nighttime temperatures may only be in the 60s. Same amount of radiation to both places, but that water vapor made almost a 30 to 40 degree difference sometimes in temperatures at night. You can see how important it is. The calendar effect is just a method that we've been using for years to track carbon dioxide. And you can see how swiftly it's been going up faster and faster. You can also see down here how it changes from day. Some summer, it's getting absorbed a whole lot more. Winter, it's not getting absorbed that much. So you can track it as well during that time. So with that, I wanted to show you a way to just take a quick peek at infrared radiation or albedo of radiation. Here, for example, is geocolor, which is we are just seeing as if your eyes were looking down from the satellite. That is what we're looking at right now. There are several other places we can look, the wavelengths we look at. Matter of fact, we write red and blue wavelengths out of it. Blue visible, red visible. Here is a band of infrared radiation that actually looks at kind of more of the vegetation. Can be used for that. Here's another one that kind of indicates, oh, this is where the cirrus clouds or high clouds are. Maybe we look at cloud particles. These are different wavelengths in infrared coming out from the Earth. Here's upper level water vapor. Here's mid or lower level. Kind of a nice thing to know if you're forecasting the weather. So all of these are different ways we take advantage of knowing what different wavelengths and how they impact and where they might be coming from in the atmosphere. So that's what I wanted to get to you now today. Let me know if you have any questions about this.